Hey everybody, we're starting section 2.5, the fundamental theorem of algebra today, and we're going to start something new. Hopefully you downloaded the note-taking guide for you so that I'm just kind of feeling like I want you guys to absorb more, write less. So we're just going to try it, see how you like it, and get some feedback, and then we can continue with this if you like it, and if not, we can go back to the old way. So anyway, hopefully you either printed this out or you've downloaded it and it's on your tablet so you can write on it or however you want to do it, okay? So here we go. So in this lesson, we're learning how to determine the numbers of zeros in polynomial functions and find them, okay? So our important vocab, first one is the fundamental theorem of algebra, and that says if f of x is a degree n, where n is greater than 0, so we can't have it be a negative, right? We can't have a negative degree, and we can't have a 0. Then f, or the function, has at least 1 0 in the complex number system. Okay. And then our linear factorization theorem says this. If f of x is a polynomial with a degree of n, okay, so again, where n is greater than 0, then f has n number of factors, okay? So, and conjugates are, if something is in the form a plus bi, its conjugate is a minus bi. So those are important vocabs. Okay, and if you're looking to follow along, you can look at this on page 135 in your book. It says the fundamental theorem of algebra in the complex number system, every nth, now that's just whatever the highest exponent is, nth degree polynomial, has the same number, n zeros. So the nth degree matches the number of zeros that we have. So for example, how many zeros does the polynomial function 5 minus 2x squared plus 3x cubed minus 12x to the 5 have? So keep in mind, we can write this in descending order. We can say negative 12x to the 5 plus x cubed minus 2x squared plus 5. We know our degree is the highest exponent, which is 5. So we knew by our fundamental theorem of calculus, or of algebra, that, or rather, the linear factorization theorem says that if it has a degree of n or 5, then it has the same number of factors or zeros, because factors and zeros go hand in hand. So then it has 5 zeros as well, because we know a factor looks like x minus some value of k, where the 0 or the solution is k. Okay, so factors and zeros go hand in hand. Okay. All right, and an nth degree polynomial can be factored into n factors. So however, whatever number of solutions we have the same number of factors. Again, factors and solutions go hand in hand. All right, let's look at this next one. Finding zeros of a polynomial function. Remember that the n zeros of a polynomial function can be real or complex, and they may be repeated. Okay, so the zeros, aka solutions, roots, and x-intercepts, Okay, those are all the same words. Of a polynomial function can be real or complex, and they can be repeated. Remember, that's what we called a multiplicity. Okay, so for example number 2, we're going to list all of the zeros of the polynomial function f of x equals x cubed minus 2x squared plus 36x minus 72. So remember when we looked at this where we said this last term is our p value, this first term is our q value, and we're going to list all of our possible values, possible roots. And so we look at the factors of p and the factors of q. The factors of this p are really, really big. We've got plus or minus 1, plus or minus 2, which actually 1 goes with 72, plus or minus 2 goes with 36, plus or minus 3 goes with, let's look, 24. And then we've got 72 divided by 4 is plus or minus 4 and 18. And I'm just kind of putting them in groups of, and pairs of their factors. And then we have plus or minus 6 and plus or minus 12. We're getting closer. And then plus or minus 8 and plus or minus 9. Whew! So that's our huge long list, whereas Q only has plus or minus 1. So all of our possible roots are, remember, every value of P over every value of Q, which is really, in this case, just our list of our factors of P. Now, if you wanted a starting place, you could also look at the graph, and it can give you kind of a hint for what one of the first zeros will be. So I'm going to try 2 first, okay, which is one of our roots right here. And we're going to put down our coefficients. So our coefficients are 1, negative 2, 36, and 72. And we're going to bring down the first term, and now we do synthetic. 2 times 1 is 2, add down. 2 times 0 is 0, add down. 2 times 36 is 72, add down. This is our remainder. So we know 2 is a solution if the remainder is 0. So we know 2 is a solution. And now we have this left, which is a quadratic. Okay, this tells me we're left with 1x squared plus 0x plus 36. So we're going to use this and use the quadratic formula to find the other zeros. And so we're going to say negative b plus or minus the square root of b squared minus 4ac all over 2a. And we get plus or minus root of negative 144 all over 2, which I know the root of 144 is 12, so the root of negative 144 is 12i because of that negative in the root. And then we get plus or minus 6i. So all of our zeros are plus or minus 6i. And the 2 that we found. And so look, we had plus 6i, negative 6i, and 2. So there are 3 roots, and look at this. Our highest degree was 3, so we expected to have 3 roots. All right, let's talk about conjugate pairs. Conjugate pairs say this. If a plus bi, where b is not equal to 0, is the 0 of a function, then the conjugate, which is a minus bi, is also a 0 of the function. So here's the deal, friends. If you have an imaginary root, the conjugate of the imaginary root is also a root. They always come in pairs. So where there is one, there's always another one, okay? So anytime a root is complex or imaginary, the conjugate is also a root. They come in pairs. Okay? This is really important. Okay, so let's talk about factoring a polynomial. Okay? So to write a polynomial of a degree where n is greater than 0 with real coefficients as a product without complex factors. So if I don't want to have a complex value like I, okay, or a plus bi, here's what we have to do. We're going to write the polynomial as a product of linear and quadratic, because remember, if we're going to have complex roots, it's going to come from the quadratic leftover factors. So again, if we want to write them without complex factors, you have to use linear, which would give you your real solutions, and quadratic factors, which could give you a real solution, but often give you imaginary solutions. And a quadratic factor with no real zeros is said to be prime. Okay, here's one of our last examples. It says write the polynomial f of x is x to the fourth plus 5x squared minus 36 as the product of linear factors and quadratic factors that are irreducible over the reals. Here's what that means. They want you to put this in factored form, but not with complex factors. Okay, so here is what we're going to do. We're still going to make our list of possible roots. So here's our p and our q value. Our list of factors of p are plus and minus 1 at plus or minus 36, plus or minus 2 and plus or minus 18, plus or minus 3 and plus or minus 12, and then we also have plus or minus 6. 6 times 6 is 36, okay? And then for our q, we only have plus or minus 1. So for our possible list of roots, it's just going to be the values of p, because p over q, where q is just 1, we're just looking at this whole list of possible roots is just the list in the p factors. Okay, so this is when I would say Mrs. Salz is going to give you a help. I'm not going to ask you to run through 18 different values before you find a root. I'm going to give you a help. I'm going to say, why don't you start off and try a value like 2 first. Okay, so I'm always going to give you a hint because I'm not interested in you wasting your time. So let's try 2. To verify if 2 is a root, we're going to put 2 in the box for our synthetic division, and then we're going to come back up here to our original factor and write our coefficients down. Now remember, this one is missing an x cubed term and an x term, so we're going to put those zeros as placeholders. And here we go. We're going to go 1, 0 for the 0x cubed, 5 for the 5x squared, 0 for the 0x, and negative 36 for that last term. We're going to bring down that first term, and we go 2 times 1 is 2, add down. 2 times 2 is 4, add down. 2 times 9 is 18, add down. 2 times 18 is 36, add down. This is our remainder. So this 2 is definitely a root. Now, this gives me what we have left, right? This is 1x cubed plus 2x squared plus 9x plus 18, but that's not a quadratic. So I would say, Mrs. Salz would give you a help. I want you to try negative 2 and see what happens. So we're going to try negative 2, and we're going to try it with 1, 2, 9, and 18. Do not go back to the original function. Use the factor that's left over. And we're going to synthetic divide again. Bring down the 1. 2 times 1 is negative 2. I should say negative 2 times 1 is negative 2. Add down. Negative 2 times 0 is 0. Add down. Negative 2 times 19 is negative 18. Add down. This again is our remainder. So this is a root. Now we have 1x squared plus 0x plus 9 is left. This is our quadratic term that we're going to solve the rest of the roots. So I know x squared plus 9 equals 0 is going to give me the rest of my solutions. If I subtract 9, I get x squared equals negative 9. Plus or minus the square root on both sides, and we get x equals plus or minus 3i. Okay, now remember, I didn't want to have a root where it was complex numbers. So we needed to actually stop. Go ahead, and we're going to stop right here. So our factors are x minus this root here that we just found, 2, x minus right here, we tried it and it said it was negative 2, and then this is what we had left over in terms of a quadratic form, which we're talking about right here. This is going to be our x squared plus 9, and that's our list of factors, okay, that we didn't want them to have complex numbers. Now, in completely factored form, so our completely factored form, we would have the same factors, but instead of this x squared plus 9, we're going to put that in using our roots. So we'd get x minus 2, x plus 2, x minus positive 3i, and x minus negative 3i. So we're left with x minus 2, x plus 2, x minus 3i, x plus 3i. And that is our completely factored form where we have 1, 2, 3, 4 roots. And if we look at our highest term on our function, it's a 4. So we knew we would have 4 roots. Okay. And the reason why we cannot graph to use complex zeros is because complex numbers are imaginary. So imaginary roots don't cross on the x-axis, okay? That's all of our notes for today. I'll see you back in class, and we'll talk about how that was for you.